In 1543, Nicholas Copernicus published his book On the Revolutions of the Celestial Spheres, shortly before his death. His publication proposed a detailed model of the solar system, one that was unheard of up until this point. Copernicus had proposed the heliocentric model for our solar system. As we understand today, this model is accurate, and we live in a solar system of 8 planets. However, we also know that these are not the only planets out in the universe. Planets outside of our solar system are what we call exoplanets. One particular exoplanet orbits a host star approximately 94 parsecs away, and will be the focus of this project. This is HD 224693b, a planet that our group hypothesizes will be uninhabitable. Let's take a closer look. HD 224693b is a confirmed planet discovered in 2006 via Doppler spectroscopy. Doppler spectroscopy is also commonly known as the radial velocity method or the wobble method. This method of discovery fundamentally relies on observations of the host star's color. Doppler shift is the apparent change in frequency of a wave due to motion between either the observer, the object being observed, or perhaps both. In the case of stars, the waves being observed are light waves. The visible portion of the electromagnetic spectrum can be split into various colors of light, with each color corresponding to its own wavelength. When a wave source approaches the point of observation, the wavelengths are compressed and blue shift occurs. When a wave source drifts away from its point of observation, red shift occurs, because its wavelengths are stretched out. The changes between red and blue shift can be observed in a host star. This shifting is caused by the force of gravity between a host star and its planet. While the planet is obviously able to orbit the star because of this, an equal force is exerted upon the star by the planet, causing this tiny wobble, which astronomers can use to determine the mass of the planet. Due to it being so far away, very little is known about our exoplanet, but we can make some educated guesses about its potential habitability based on its host star. For starters, we can identify our exoplanet's creatively named host star as a G-type yellow main sequence star. This star resembles our own sun pretty well, but burns a bit hotter and a bit brighter. Using a Hertzsprung-Russell diagram, we can plot our host star around here, and approximate its luminosity to that of our own sun. Since we don't know enough about our exoplanet, we can simulate it as a black body, and compare it to a version of itself with Earth's conditions. A black body is a featureless planet that perfectly absorbs and perfectly emits all energy that interacts with it. For this, we will be using the Mini-GBIT 2017 simulation, which provides a planet's average surface temperature based on the luminosity of a host star, the distance from the planet to its star, the planet's albedo or surface reflectivity, and the planet's greenhouse effect. Sources of error in this model are the product of its simplicity. This model uses average values for distance between the star and a planet, surface reflectivity, and surface temperature. The model doesn't take into account the possibility of a more elliptical orbit, where the distance from the planet to its host star could have drastic range, nor does it take into account that particular regions of a planet could have varying reflectivities of its host star's light. The output of the model also only provides a global annual average temperature, not truly reflecting the climate of different regions on the planet's surface. Without further ado, we will go on to plug in a fifth of an AU as our distance from the star and leave luminosity the same. Our outputted surface temperature is nearly 10 times that of Earth's, with its albedo and greenhouse value factored in. If we update the model to give our exoplanet Earth's atmosphere and reflectivity, we'll see that the average surface temperature only climbs, nearly to the melting point of lead. When dealing with habitability, there's always so much more than just determining the temperature of the planet's surface. Playing around with the albedo, we found that in order to keep a similar average global annual temperature, our exoplanet must have an albedo of nearly 94%, meaning an overwhelming amount of energy must be reflected, not to mention the question of whether there is an atmosphere or if it is breathable. If we were to colonize this planet, our own biological processes, as well as the products of technological use, could contribute to the presence of greenhouse gases in the atmosphere. Many more questions of habitability arise, such as whether there is enough mantle activity to provide a magnetosphere that would protect the surface from harmful radiation produced by the host star. There is no guarantee of the planet's seasonal conditions, as we don't know its axial tilt. It appears that the biggest deal breaker for us humans is the fact that this exoplanet is extremely close to its star, far out of its Goldilocks zone. However, this is not to say that life cannot exist on this distant world. It is insanely ambitious to even think about inhabiting another planet when evolution has groomed us to thrive specifically in Earth's conditions. About 307 light-years away, we lack both the technology and economy to support such an adventure, even if it was habitable. In conclusion, it's pretty safe to bet against your survival on the planet HD 224693b, due to its unwelcoming climate of scorching temperatures. All sources used in the making of this video can be found in the description, and I hope you enjoyed it. Thank you for watching.